In an earlier video, I showed how to make an XY scatter plot of the Arrhenius equation. In this video, I want to explain the equation and actually find the activation energy of a reaction from the Arrhenius equation. Here's the Arrhenius equation. It shows the rate constant, K, of a reaction is equal to E raised to the negative EA over RT. EA is the activation energy. R is the gas law constant or universal gas constant. And this gas constant is in terms of joules per Kelvin mole. And T is the temperature in Kelvin. Just a quick word on the activation energy. The activation energy is the barrier between the reactants and the products. In other words, molecules have to collide with each other with enough energy to get over this barrier and reach the top of the curve, which is the transition state. The A term is called the frequency factor, which is basically the fraction of molecules that actually collide with the correct orientation and how often they collide. As I showed in my earlier video, if I plot the rate constant versus the temperature, we would see an exponential growth. And this makes sense. The rate constant is exponentially dependent on the temperature. But what if we wanted to find the activation energy, EA, of this reaction? We can simplify this equation to do this. And here's how we do it. If I take the natural log of both sides, I would get the ln of k, the ln of A, plus the ln of E raised to the negative EA. This is one of the rules of natural logs. When you have a multiplication here, that will get separated with an addition sign. And of course, the natural log times the exponential, the E term, will cancel. And so we can rewrite this. Ln of k is equal to ln of A minus EA over RT. Now let me move this around just a little bit. Ln of k is equal to minus activation energy over R, and I'm going to separate the T here. So we'll multiply by 1 over T, separate this term, plus ln of A. And if you look closely, you'll find something interesting. This turns into a really nice simple equation, y equals mx plus b. So by plotting the natural log of k versus x, which in this case is 1 over t, should give us a straight line. So let's go ahead and show that. So here's my Excel file from my last video where I actually showed how to plot the Arrhenius equation, and I just took some sample data here, just some generic data, just to show you the exponential curve here. Well, what I'm showing you now is let's redo this. Let's plot the natural log of k versus 1 over the temperature. So I'm taking the original data for this exponential curve, and let's get 1 over the temperature. So in Excel, this is how we do it. I'll press equal 1 slash or 1 divided by this cell, the 100 Kelvin, and I'll press enter, and that'll give me 1 over 100. And I want to do this all the way down this column with the rest of the temperature data. I'll click this box here in the right bottom corner, Click and drag down, and that will give me 1 over the temperatures. So now let's do the natural log of the rate constant K. So right here I'll press equal, just type in the letters ln, open parentheses, I'll click the cell here for the rate constant and close the parentheses and press enter. And so that's going to do the calculation for me. Here's the other shortcut I've shown in my other videos. In the bottom right hand corner, when you get the black cross here, just double click. You can click and drag, but you can double click and it'll do the calculation for you. Okay, so pretty simple. Here we go. Let's highlight both columns, and this will give us a plot of the x-axis, 1 over t, versus the y-axis, the ln of k. So up at the top, you can click Insert, and in the center, you'll see the XY scatter. And I'll just go ahead and pick something with this line here. Yeah, really beautiful. There you go. And so that's how we get a nice linear graph. So let's go back and find the activation energy. We can see that this equation gives a straight line, y equals mx plus b. We know that the line has a negative slope, and the slope is the activation energy over R. So here's the straight line of the plot of ln of k versus 1 over t. And a common way to find the activation energy is just to take different data points and find the slope. So if I just take 2 data points, we'll just call this 1 and 2. This would be the natural log of the rate constant 2 at temperature 2. And this would be ln of K1, the rate constant at temperature 1. And if we subtract these equations, we can find the slope. So here are the 2 equations subtracting. The rule with natural logs is when we subtract, this becomes the natural log of K2 over K1. And right here, this gets pretty messy. So let's go through this slowly and just rewrite this equation. Let's distribute this negative sign. So I'm just going to rewrite everything. And I'll distribute this negative sign, so this becomes a plus. Activation energy over R, 1 over T, minus ln of A. And so the first thing that pops out, of course, you have a plus ln of A and a minus ln of A. So those terms will cancel. And we're left with this section right here. Let's factor out EA over R. And you'll notice you'll have that negative term still here. And this is a positive term. So notice this becomes 1 over T1 minus 1 over T2. And we have it. So using this equation, if we know the 2 rate constants at the 2 temperatures, we can just plug into this equation. R is a constant, and then we can solve for our activation energy. On the other hand, using this equation, if you're ever given the activation energy at some temperature, you can always go solve for a rate constant, as long as you know the rate constant at some other temperature. You can also solve for a temperature if you're given the 2 rate constants and the activation energy. So let's do an example. For some reaction at 27 Celsius, the rate constant is found to be 1.2 times 10 raised to the 10 liter per mole second. A second experiment at 52 Celsius exhibits a rate constant of 1.69 times 10 raised to the 10 liter per mole second. What is the activation energy in kilojoules per mole? Right here, the first thing I'll do is I'll convert these into Kelvin. So for our temperatures in thermodynamics, we do need to convert to Kelvin. So I'll add 273. And so this becomes 300K and 325K. It's up to you how you want to approach this. I'm a big advocate of just getting what you want by itself. So in this case, for example, I'll divide both sides by the temperatures, or 1 over the temperatures. So of course, these temperature terms will cancel and multiply both sides by the gas law constant. And of course, these terms will cancel. It looks pretty messy, but let's go ahead and rewrite this. So a few things to note here. Inside the natural log, these terms, these units will cancel. And all we have to do now is plug and chug. Let's get some values for our terms. So in the natural log right here, I'll show you my calculator. So the natural log function will be somewhere in here. This is where I have it here, the ln. Be careful not to use the log function. That's not what we're doing here. We're using the ln function. So I'll press ln and just plug in the ratio, 1.69, 10 raised to the 10 over 1.2, 10 raised to the 10. So to two significant figures, this turns out to be 0.34. Now this is just a number. Remember, those units cancel. And now let's get the temperature. And I'll go ahead and plug it in this way. In parentheses, I'll plug in 1 over 300, close parentheses, minus 1 over 325 Kelvin. And so that's going to get me a value here. I'll go ahead and write this in scientific notation, a little bit easier to see. And notice my Kelvin is inverse. I guess I probably should have gone to 3 sig figs, but that's okay for right now. I'm going to be reporting this as two significant figures at the end anyways. Okay, so this looks a little confusing. Remember, this is in the denominator as well. Let me go ahead and rewrite that. Remember, this is joule over Kelvin mole. And so I'll rewrite this. I'll put the Kelvin mole in the denominator with my temperature term. And of course, you see what happens here. The kelvins will cancel. And take a look at the units. The units left over, joule per mole, which makes sense. These are the units for activation energy. And let's go ahead and get a number. So here's the value I get. 1.1 times 10 raised to the 4 joule per mole. Now, the question is asking for the answer in kilojoules per mole. So all I have to do just a little bit of legwork here. And we'll do a simple conversion to kilojoule, cancel the unit of joule. and there are 1,000 joules in 1 kilojoule. And so this gives us an activation energy of 11 kilojoules per mole. Let's close with this example. For some reaction at 25 Celsius, the rate constant is found to be 6.45 times 10 raised to the negative 6 liter per mole second. The activation energy is 67.1 kilojoules per mole. A second experiment at 38 Celsius is carried out. What is the rate constant in liter per mole second at this temperature? All right, so here's our Arrhenius equation. We have our two temperatures. The temperatures are in Celsius, so we'll have to convert that temperature, or each temperature, to Kelvin. So we'll add 273. Be careful with your significant figures. Since these have 0 decimal places, I'll just add 273. 298K, and this comes out to 311K. Now, this is an interesting question. You see, in our last example, we were looking for the activation energy, but in this case, they actually give us the activation energy for the first experiment. And what they're asking is, when we change the temperature or increase the temperature, what happens to the rate constant? So the first rate constant, K1, is given to us, and what we're doing is we're looking for the second rate constant. So a couple things we have to do here. Number one, recall that R is our universal gas constant. So this is 8.314 joule per Kelvin mole. Now R is in terms of joules. Our activation energy, on the other hand, is given to us in terms of kilojoules per mole, 67.1. So we'll have to convert one or the other. I'll convert the activation energy. So our kilojoules cancel, so this just is multiplied by 1,000. So now we can plug and chug and solve for the second rate constant. Now for right now, I'll go ahead and solve the right-hand side first. I'll leave the rate constant terms alone for right now. And so when I plug these values in, we'll get some numbers. And now I'll plug in the temperatures. So this is what we have so far. I'll check the units. You'll notice the joules cancel here, the mole over mole cancels here. We have Kelvin in the denominator of a denominator, and by rule, this unit will come up to the top, which makes sense because we're going to multiply that by inverse Kelvin. When we plug these numbers in, this term right here is 8.07, 10 raised to the 3, and again, this is Kelvin. The unit Kelvin comes up to the top. And we have to be careful here. So this is 1 over 298 minus 1 over 311. These terms are 1.40 times 10 raised to the minus 4, and Kelvin is in the denominator, so this will be inverse Kelvin. And of course, we're multiplying, so this makes sense. These units will cancel. So let's put this together. This term times this term is 1.13. No units. We'll get our units when we get our rate constant here in just a minute. Now, This is a natural log, and so for students that haven't seen this yet in general chemistry, um, we have to get out of this natural log. And so the way to do that by rule here is just put an e down here. And so this is e raised to the whole thing. So e raised to the natural log is just 1. So that cancels. But we have to do it to the other side as well. And so this term is going to be e raised to the 1.13. And so notice what happens here. Everything inside the natural log just comes out like you would in algebra here. So this is just k2 over k1. And this is equal to e raised to the 1.13. Now let me show you this for students that haven't seen this before. If you look closely here, you'll see the natural log, ln. And right above that, it might be hard to see here on this calculator, but you'll see that e raised to the x right in here. So we'll have to do a second function and get that e raised to the x. Let me show you how to do that. So I'll press second natural log, and you see that e comes out. So this is e raised to the 1.1, whoops. So this is e raised to the 1.13. And the answer here is 3.095. I'll go ahead and round that to a 3.10. No units. And so here's where we finalize our problem. We'll multiply both sides by k1, and we'll solve for k2. K1 is given to us at the beginning of the problem, 6.45 times 10 raised to the minus 6 liter per mole second. So I'll type that or write that here. You can see that's where we're going to get our units from. And when we plug this in, I'll go to 3 significant figures, 2.00 times 10 raised to the minus 5 liter per mole second. Let's think about this for a second. So this makes sense. So at 25 Celsius, we have some rate constant, 6.45 times 10 raised to the minus 6. And when we increase the temperature, we expect an increase in the rate constant. According to the Arrhenius equation, we expect an exponential increase. And so when we go to the higher temperature, 38 Celsius, we do see that this rate constant increases, 2.0 times 10 raised to the negative 5, of course. Negative 5 is bigger than 10 raised to the negative 6. 10 to the negative 5 is bigger than 10 raised to the negative 6. So this makes sense.